schedule this Wednesday. This Wednesday, 10 a.m. Go into my calendar from 10 a.m. to 12:50 p.m. So you have 2 hours and 50 minutes for the final exams. Okay. Question is here. 3 problems. As usual, I was thinking over the weekend whether it's open book, open note, or closed book, closed note. I prefer closed book, closed note, like midterm exam. The reason is easy exam can be defined. If I do give you open book, open notes, I will make sure problems are not the same as my lecture notes, right? So you cannot copy from the book, from the note directly. That means the level of difficulty may go up. I need to design something you may not easily copy from the notes. So I prefer closed book, closed note, just like a midterm exam. I assume you don't know what I do. If you do, you hit the lottery, the problem can be very easy, straightforward like my lecture. Right, so that's my intent. Unless you disagree, majority of people disagree, then we change to open book, open notes. Questions?
Do we still get a formula sheet as close?
So yeah, same as before, so 1 page front and back you can write. You may need to modify your questions, problems. I just want to make sure you don't know what I'm going to ask you. So I feel free to design anything, just pick up on my lecture. That's my intent. Intent is clear. If I do not hear that anybody object to this idea, if you do, please raise your hand. If not, close book 3 problems, close book, close notes exam. Okay? And for sure, you can bring the 1 page of paper, write down the equations or anything you want to write. Okay? Like a midterm exam. Right? So I perceive exam will be straightforward. I told you last time, my problem is from chapter 3, right? Chapter 3, one problem from chapter 4. Because chapter 3 is the DC MOSFET analysis, right? And chapter 4 is AC MOSFET amplified. Okay? So 2 problems are clear, format-wise, from chapter 3, chapter 4. To be more specific, DC analysis for MOSFET means IDS, VDSQ. Similar to BJT, drain current, right? Collector current, so in MOSFET is drain current, DC analysis, gate source loop, finding IDSQ. Or VDSQ, which is just drain the source loop based on IDSQ you already determined. So that's DC analysis. It can be any circuitry. It can be classical common source amplifier, common gate amplifier, common drain amplifier, but it's a DC analysis amplifies capacitance open circuit. So you may lose AC amplifier, but for DC analysis, you just look at DC equivalent circuit, right? That's a hint. Okay. You may see different drawing, but DC analysis, assuming capacitance are open circuit. Right. Okay, so yeah. Okay, some people may read my mind, some people don't, but I gave you the information already. Right? Okay, so AC analysis, 3 different amplifiers. For sure, towns, right? Common source amplifier, common gate amplifier, common drain amplifier, 3 classical amplifier, could be input resistance, output resistance, small signal voltage gain. So that's quite standard analysis, okay? Standard analysis, AC analysis. So to me, chapter 3, chapter 4 are reflection of BJT, DC analysis, BJT amplifier. You just use a MOSFET transistor, currents and technology, slightly modification about equivalent circuit. So if you didn't do BJT amplifier well, you have a chance to recover for FET amplifier. Right? Third problem can be from chapter 1, chapter 2, chapter 5, chapter 6. Okay? So one problem coming from those 4 chapters. Not determined yet. 4 chapter, only one problem, so I'm going to pick up one, right, to ask you. So, but those 4 chapters you already had in your midterm exam. Okay? So 2 problems clearly defined, 1 problem from your midterm exam. Yeah.
So
Question?
chapter 1 and 2 is like the basic, like,
Very basic.
and then 5 and 6 was the
BJT, DC, BJT, AC analysis. Yeah. Okay. So that's what I see. Should be very straightforward. Yeah. So that's what I see now. So format is clear, 2 hours and 50 minutes. And you may need some calculation for this chapter, right? Chapter 3 DC analysis, drain current, solving drain current equation, you may need a calculator. For BJT, I remember you don't even need compute much, okay? But for chapter 3, you may need to solve quadratic equation, remember? Solving quadratic equation, so you do need a calculator, but it's not big deal. Again, my policy remains the same. I need to see your equation, equivalent circuit analysis, even though you do not get correct answer, but I check your analysis, your equation, I can give majority of the credit, partial credit, right? So if you just show me the answer without the procedure and process, not good. I may take some penalty there. Alright, so the key point is clear. Understanding DC analysis, AC analysis, equivalent circuit equations, and then computation. In case your computation is not right, but the equation is right, analysis right, you already get maybe more than 60%. Right? Okay. Exceptions. You tell me the answer is 2n, then I'm bothered by that answer, for example, right? So anything could be on the order of median, not on n, right? So that's the only thing I want to make sure you know the range, okay? The range and so on. Yeah, so that's what I can share with you in terms of format and so on. So open for any questions you may want to ask today. Questions?
Were you saying we can use a computer to solve the quadratic equations, or?
I prefer not. You don't need a computer. You need a calculator. Right? So quadratic equations should be very straightforward. Ax squared plus bx plus c equal to 0. The answer is standard minus b plus minus square root divides 2a, something like that. So you can use standard equation, find out the result. So I don't believe you need a computer. That's overkill. That's overkill. Yeah. Computer solving 1 plus 1 over years. Okay. Again, it's not computation itself. It's really the concept. It's really the analysis that I check. When I do grading, I don't use computer. I just look at your answer visually. Simple computation in mind. Usually that's the case, unless I really need to use calculator, compute the number, and so on. So you can imagine, on my shoes, I look at your result, how do I analyze your result for credit? So, yeah. All right. Any other questions you may have today? No? Good. So last call. Any more questions for me to address? This is Q&A. If there's no question, there's no answer.
I mean, would you be able to like run through a MOSFET problem real quick?
Yeah.
Just like a general one?
Okay. I will go back to the note,
Yeah.
which is the same thing. I anticipate this question, so that's why I bring my note. Repetition, to me it's repetition, but you ask me, I need to do my job. Any p-type, that's good questions. You know, I prefer n-type. Yeah, I prefer n-type because faster to analyze the grade, to do everything. If I give you a p-type, you slow down, my grading slow down, everything slow down. Yeah, so n-type most likely, p-type I consider unusual, unless I want you to slow down. Most of the time, only takes n-type. That's a good question. Okay, so example, right? So example for APT. So let me use this one I presented in class to show you example. Alright, so it's a good question because not everyone in the classroom should know, right? So that's a good example to ask. 6 kilo ohms. 6 kilo ohms, BT 1 volts, 10 mega ohms, 10 mega ohms, and VA goes to infinity, K, which is defined by mu NC outside W over 2L equal 1 half a million over volt square. So what is Q? This is ideal Q. So then by Thanksgiving, and RS giving.
Is it grounded?
This is ground.
Okay.
Yeah. K, also called transconductance factors, is equal to 1/2 milliamp per volt square. That's a unit. Milliamp. Pay attention to the units, milliamp per volt square. And what is IDSQ? So we need drain source loop. Remember, we need the drain source loop. So in the drain source loop, we have also called VGG, RG, VGS, RS, VDD, RD to ground. So we have drain source loop. Okay? So I have equivalent circuit. This is equivalent circuit, DC equivalent circuit, and we have a gate source loop similar to a BJT phase emitter loop. The gate current is 0. Questions?
So for the final, would you want us to write that as well, like that circuit?
Good questions. If you don't write this equivalent circuit, at least you know you write VGG minus VGS minus IDS RS equal to 0. I know you know this equivalent circuit. We saw this equation that's missing. Okay. So IG is equal to 0. That's why I can use the VGG directly. Okay. So VGG minus VGS minus IDSQ RS equal to 0. And, for sure VGG equal to 5 volts, right? So it's divider, 10 volt, R1, R2 the same, VGG, 5 volts. So, another equation, IDSQ is equal to K, VGS minus VT squared. VA goes to infinity, we neglect what's called channel length modulation effect. So, I have two equations, two unknown. Right? VGS is not known, IDS is not known. Two equations, two unknown. This is known, this is known, VGS not known, IDS not known. In this equation, VGG is known, VGS, RS is known, VGS, IDS not known. So two equations, two unknown. You combine it, you have quadratic equation.
If the modulation effect is not neglected, then we.
You have two equations, three unknowns. Right. So if VA is not neglected, you have two equations, three unknowns. So how people solve the problem in real world, they use iteration technique. Assume VA infinity solve the problem and then solve the equation again. So many iterations until the result are converted. So when you have two equations, three unknowns, you have to use numerical method, such as iteration technique. Take initial guess, solve it, keep going, convert. After a few iterations, you get the result. May not be good for the final result.
Yeah, so like for the DC analysis, we can assume that this voltage will be.
So I probably will specify for you, if I didn't write, you can assume. So anything I say, you have to use it. If I do not say it, you can make an assumption. Then I know what you're solving the problem for. So most likely I will tell you unless I forget. Okay. More questions to this point? Three already over there.
So in this circuit, was this the one where like RG doesn't have any current? Is that what this circuit was?
So this one I'm not done yet because I try to answer all the questions. This is DC analysis. I have two equations. I will continue to complete the analysis. But I already saw 3 or 4 questions already, so try to entertain the questions. So something need to trigger your question. This is one. The solution.
How did you get VGG equals 5?
The dark blue behind you. He raised hands multiple times. Go ahead.
I was just gonna say, if VA is not infinity, where would it be included in these two equations?
Good question. If the VA is not infinity, remember 1 plus VGS over VA, you need to have this bottom right hand turn if the VA is not infinity.
So that would be multiplied by,
Times this.
okay.
So I have two equations, 3 unknown because we don't know VDSQ, we don't know IDSQ, we do not know VGA. So then 2 equations, 3 unknown.
How would this change if there's a VS at the bottom instead of that being ground?
Also good question. How does it change VS? VS could be VSS, then your equation will be VGG minus VGS minus IDSI minus VSS equal to 0.
And how does VGG change?
Also very good questions. If that change, you have VDD minus VSS divides 20 million times 10 million, that is this ohms loss plus VSA, just like a BJT.
Okay.
Yeah. So if VSS is not equal to 0, then one more time you need to put the VDD minus VSS, which is potential difference, divides total resistance, that's current. Current times 10 million is total drop across this resistance. and that voltage drop on top of VSA is VGG. So if VSA is not equal to 0, good question you asked, it changed VGG. It also changed the gate source loop equation. It also changed drain source equation, right? So all these equations are factored in similar to BJT. I believe those equations are also in your textbook. So, very good question. Multiple hands. Let me entertain there at the back question.
So to get VGG, you treat the gate branch like there's no current. Do you always do that?
Yeah, because IG is equal to 0, that's gate oxide.
Okay, for all MOSFET circuits?
For all MOSFET, you are correct. For MOSFET, gate oxide, gate current is 0. Yeah, different from BJT.
So if VDD and VSS are the same, then VGG is zero.
If VDD VSA is the same, transistor is cut off. Right. If VDD VSA is the same,
Yeah.
then transistor is cut off because VDS is equal to 0. No way you can turn on the transistor. Must be VDD 10 volt, VSS may be minus 10 volt. If VDD 10 volt, VSS 10 volt, potential difference 0, nothing happened. Current 0. Device is cut off. So 10 volts minus 10 volts, the difference 20 volts. So in that case, the midpoint 0. Right, 10 minus 10, 0 here. Yeah.
Do you want us to always assume pinch off? Like the VGS minus VT squared, or?
Yeah, also good question. We'll assume is transistor is in saturation region and then solve for the equation. And in theory, it should lead to correct answer. If not, I need to use the linear region equation, redo it, and find out the answer. Yeah, because I have to make there are two possibilities. I have to make a choice, either in saturation region or linear region. I need to make a choice, otherwise I cannot continue. So most likely we assume saturation region, solve for the problem, and then say consistent check. I will complete this problem for 100% understanding. We'll do safe consistent check, we get the correct answer, done. If not, need to redo it, assume linear region equation, and then safe consistent check. Hopefully, you get the correct answer. If not, both problems do not lead to correct answer, you have a problem, maybe numerical error in your computations.
Why don't we include RG in the equation?
Say it again.
Why don't we include RG in the equation?
Because IG is equal to 0, IG times RG is equal to 0, so that's why I do not put RG in the equation.
No, RD, the drain resistance.
RD?
Yeah.
RD, I heard RG. So RD is here in the gate source loop, RD is not in the loop. So in the gate source loop, RD is not in the equivalent circuit. But in drain source loop, RD is in the equivalent circuit. In other words, if I want to find out VDS Q is equal to VDD minus RD plus RS times IDS. If VS is equal to 0, if VS is not equal to 0, then minus VSS.
Okay.
So that's the equation I need to use from drain source loop. Right? Okay, so you'll probably see why I want you to write the equation. Because from the equation, I know whether you already consider VSS, drain source loop, gate source loop. So equation should be right, I know you begin with right analysis. And then you solve quadratic equation, and some people may screw up a quadratic equation, right? So depending on how you solve your problem, I perceive how many percent you should get from your partial credit. So again, good advice, always write down equation, okay? And then solve numerical answers and so on, right? Do not just give me an answer without an equation. Equation means analysis, means whether you understand the problem. Like what he asked me about VSS. If I could give you VSS, you do not write down the right equation, I know you didn't consider VSS already. So that's the way I analyze the problem. Okay, so continue the analysis, make sure everyone understands numerical computation clearly. So after I have two equations, two unknown, I will find the quadratic equation. Just merge those two equations and have quadratic equation. By the way, ID is on the order of median. So I have ID on the order of median. So I will have a quadratic equation. Okay. Why I use median? Because if I do not use median, I use absolute value. This RS is kilo ohms, right? Kilo ohms times very tiny number, your quadratic equation will have very small number, very big number, and so on. So if you put all the resistance in kilo ohms, all the current median in simple number, and that's what we lead this quadratic equation. So in this quadratic equation, two answers, ID is equal, IDS is equal to 89 million or 0.5 million. So quadratic equation, as you know, two answers, two roots. So in math, I have two answers. In circuit, we only have one answer. Right? In circuit, there is only one answer. But in math, I have two answers. So then I need to do safe consistent check. How do I do safe consistent check? Presented before. This VS is equal to IDS times IS. This case, VSS is equal to 0, right? In this example, VSS is equal to 0. So VS is equal to IDS times RA, which is 0.89 million times 6 kilo ohm, give me 5.34 volts, greater than VGG. So if VS is greater than VGG, transistor cannot turn on. VGS is VGG minus VS. VS is greater than VGG, transistor cannot turn on. So I know this cannot be right. So 0.89 cannot be the answer. Then another check. If VS is equal to 0.5 million times 6 kilo, which is 3, so this is less than VGG, right? VGG earlier I said 5 volts, 5 volts. So this is on. So marker is on. Good job, right? So same consistent check. 0.5 million allowed my transistor to turn on. The next check, I need to check whether transistor is in saturation. He asked me, why do I make assumption for pinch-off point saturation region equation? So I need to do VDS. So VDSK, VDSQ is equal to 10 volt, which is VDD minus 0.5 million times 6 kilo plus 6 kilo, right? And then I get the what? VDS 4 volts.
Yeah.
4 volts. So 4 volts means saturation, which means the equation I used earlier is correct. Saturation means IDSQ. IDS should be equal to KNA times VGS minus VT squared. Approximation if I neglect early fact. So then my equation is also right. So this example basically tells me devices saturation. And I did assume saturation. And so then it's done. I find the answer. If I have violation, then I need to redo it. Okay, so that's how this example is carrying out. Quite a lot of safe checking point.
Can you explain again why 4 volts gives you saturation?
So usually IDSQ versus VDSQ, the saturation point is at low VDS. So early, if VDS is greater than VGS minus VT, that means saturation. Remember that equation? So usually at the low VDH. VGS minus VT, only a few volts in this case. And VG5, VS1. VS, we saw VS 0.5 times 63 volts, right? So VGS 2 volts minus 1 volt, 1 volt. So VDS is greater than 1 volt. So here is about 1 volt. 4 volts greater than 1 volt. So in this case, it's 1 volt. For BJT, that boundary point is about 0.7 volt, remember? Close to VBR. So if VC greater than 0.7 volt, for active mode. So in this case, I use this equation. Now, this is equation I determined here. This is saturation mode, and this is linear. Usually low VDH, could be 1 volt, could be 1.2 volt. It really depends on your VT and VGS and so on. Right? So that's the answer to this question.
So we had a K and a K prime. Would we have to be able to use that as well?
So I don't know your definition of K prime. Some textbook define K prime slightly different. The difference is a factor of 2. So here I define K mu n C oxide W over 2L. I define that way. I say K. Some textbooks say it's N channel Kn. Other textbook may want to define mu n C oxide W over L as a K. Then it's up to your definition. Different textbook may define K slightly different. There's a factor of 2 different. So that's why, to make it clear, I usually say K. That's my definition. So there will be no confusion no matter which book you use. So I usually define it for you so you cannot use different definition. I probably will say this for you so you cannot make your own assumption. Unless I forget. Sometimes I forget, oh, I realize I forget during the test. It happens.
I was just thinking, because I think in the homework, we had to use it maybe once or twice, but it was, I think because they gave us like the width and the length as well, so.
They give you weights and lengths, they give you mobility outside, like what I say, all these prompts are technology information. So in reality, people give you this number. But in the test, you don't have this number, I need to give to you. Yeah. So, and all this VM, UNC, oxide, WL are transistor information from technology. Designer usually get that one from our so-called library. The library itself will have all this information. They may not know, but they are there already. They just put up transistor, specify the size, and run simulation, get the result. But all the model in the simulation file has what's so-called transistor model file, and they are there to give you more complexity. There are many different levels of models for different accuracy with a different model parameter. Usually they are transparent for circuit designer, but they are required information from semiconductor technology group. they do measurement, they give you that information. Okay. So this example gives you all the numerical process for the computation and a little bit more detail compared to BJT. BJT DC analysis, if you remember, base emitter loop to find the IBQ and then ICQ, right? Faster. Okay. Right? Okay, so that's a good example. If it's AC, if you ask me AC, I may give you input capacitance, output coupling capacitance, find out, let's say, gain. This is common source amplifier gain. So then you can compute the gain. You can determine input resistance. You can determine output resistance, like what you did before. So if this AC amplifier asks you for gain, I may say, hey, please construct or write your small signal equivalent circuit, right? And then derive your gain. Because your gain, okay, so make it clear. In the textbook, there are many conditions. Some circuit may have a backpass capacitor, other circuit may not have backpass capacitor. Some circuit may have source resistance, what's called RSI. Some circuit may have load resistance. So you have RSI, RL, bypass capacitor. In the textbook, I remember you may have, especially for the BJT, you may have RE1, RE2, right? The bypass capacity in the middle. So you have many conditions. I prefer if my circuit is giving you derive equivalent circuit against that second circuit. Right? In other words, I don't want you to copy the answer from the textbook saying, hey, this is the circuit, then my answer is this, right? That's not my intent. My intent is, if I give you a specific circuit, please write down your small signal equivalent circuit according to the circuit I give to you. And then derive small signal amplifier gain easily from the equivalent circuit. Remember, VR is minus GM times VGS times effective output resistance, and then solve for the input pole and so on. So I prefer you use equivalent circuit, derive equation accordingly. Do not pick up the answer directly from the book saying, hey, this is answer for my circuit, and then I try to relate that answer to the circuit I give to you. That basically show me you don't use equivalent circuit to derive the answer. Alright. So make sure you do use equivalent circuit according to the circuit I give to you. Right? I may change location of bypass capacitor. I may change whether there's RSI, RAR, right? And I want you to derive the equation from that one and tell me the result. The matter is the gain, input resistance, output resistance. That is what I'm referring to. So then we are on the same page. You know, the problem from chapter 4, that's what I make here. I do derive many different cases. If you remember, common source amplifier, right? Common source amplifier without bypass capacitor, with bypass capacitor, with early voltage, without early voltage, quite a few different examples. Right? So, give you a circuit, that condition, please derive it. So it show me your clear understanding. That's what I want you to show me in your exam. Okay?
You do.
That's why I don't like the open book, open notes. Open book, open note, pick up, write the answer, and then tell me, hey, this is the book answer. I know it's book answer, but that's not your own analysis. Right? Clear? Not just copy the book thing, it defeats the purpose of learning. Yeah.
Could you do an example, even just for that problem of input resistance? Like the resistance?
Okay. So any input resistance, suppose this is circuit, you ask me, this is circuit, so let's say this is common source amplifier, right? And, so what is, equivalent circuit? Is, to ground, that's RG, which is R1 in parallel with R2. Right, open circuit. So this is, yeah. Right, so in that circuit, we see this, RG to ground. We are G and VGS, yeah, in this specific small signal equivalent circuit, I have VI, I have RG to ground, I have VGS open circuit. So this is current going through RS to ground, RD to ground. There's no VA, so no RR. RR is gone because early voltage is infinity. So that's equivalent circuit. So if AC analysis, we need the small signal equivalent circuit. This is small signal equivalent circuit in corresponding to this circuit. And to continue, people ask additional questions.
If VA wasn't infinity, would you have R out in parallel with RD?
Yes.
Okay.
Yes. Yeah. So he asked me if there's a, VA, then what happens? If there's a VA, there's R in parallel with this current source.
But not with RD.
He said for RD.
Oh, for RD, I say in terms, in parallel with current source, not in parallel with RD directed to ground. Unless I have a bypass capacitor. If I have bypass capacitor down, RR in parallel with RD. But in this case, if I have a VA, I have RR in parallel with this current source, but not just in parallel with RD to ground, which make the analysis more longer.
Gotcha.
So RI would be equal to RG in this case?
RI is equal to RG, that's what I'm going to say, you already said for me, that's good, so. RI, in this case, is equal to RG, correct? Because this is open circuit, that's the answer you were looking for. RI in this case, just equal to RG. RR in this case, just equal to RD. Yeah. So this is simple circuit, and more questions, 3 or 4, go back to you first.
That makes sense, but could you just explain why, like in my mind, like the input is shorted to whatever?
So because this is open circuit, remember for BJT, I have R pi, then I need to consider R pi. So this is more like RG in parallel with R infinity, with infinity, right? So RG dominant. I is more like RG in parallel with infinity. So the answer is RG. Yeah. But if that's not infinity, for BJT, I have R pi, then it's RB in parallel with R pi, plus whatever RE is there. Right? Remember, RI for BJT is RB in parallel with R pi, plus beta plus 1 times RE. Because you have second branches. This case is infinity, that's why I only see RG. So that also suggests, in this case, RI is only equal to RG. Alright, but for BJT it's different, which you already had that exams in midterm, right? Midterm ask RI. So, additional questions there? Yeah.
Could you quickly show us an example for an FET where RI wouldn't be equal to RG?
Say it again, RI is not equal to RG.
Could you quickly show us an example where RI wouldn't be equal to RG?
So in this case, because it's infinity always equal to RG, I can give you RA side, then RI, well, that's a good question. So in this case, I can add RI side, but RI is still after RI side, I still see RG. This is infinity. I equal to RG, probably in my mind, most of the circuit follow this criteria. Like what I said, I can give you RI side, but I usually, after RI side, I still see RG.
So are you saying that we're likely not gonna have a situation on the exam where RI?
If something too simple, I may not ask you. Yeah, so I consider this RI equal to RG. If I change circuit, I still get RG. Most likely, I may not test you. Right. But you understand how you solve the problem. That's most important thing. So that's what I said. I give you RSI, RI still equal to RG. So maybe I will ask you different things. Ask you different things.
Is the GM here a DC, or is it comprised?
GM is transconducting.
From the
Transconducting is determined by DC. Okay, so similar question asked by Thomas last time. GM transconductor is AC parameter, but determined by DC current. Let's say GM for the MOSFET in saturation, GM is equal to what? 2 IDS over VGS minus VT. VGS is DC biasing, VT is turn-on voltage, IDS DC current. So DC parameter determine AC parameter such as the GM, R, and so on. Yeah. So we need DC analysis to find out the numerical answer. Yeah. Right. So, questions?
Would this change if there was a VSS?
Everything changes. If there's a VSS, remember IDSQ will change. Well, IDSQ will change, GM will change based on IDSQ divides VGS minus VT. So GM equation is still the same, but VSS is added, then it changes the value of IDSQ.
But it would still like represent like the two grounded nodes right there? Like
Yeah,
that wouldn't change?
because
this way?
VSS is DC biasing, still AC ground. Still AC ground. In the small signal equivalent circuit, it's still AC ground. GM is still same equation. And AC analysis remains the same, but DC value will be different, right? IDSQ is function of VSS. So your IDS value changes, your GM value changes, but your GM equation derivative IDS against VGS, that remains the same. Your equivalent circuit remains the same because VSS is AC ground. So AC, DC, slightly different.
Is the VGS and GM VGS different?
VGS always between VG and VS.
Are those two VGSs different? Is one DC and one AC?
I'm talking about, I'm talking about AC analysis.
Yeah, it was the VGS.
So VGS is different. This VGS, in other words, if I don't have RSI, VI is VGG, right? But if I do have RSI, VI minus AC current times RSI is VGG. The result will change it. Basically, it's like RI over RSI plus RI degradation term. You see RI, RSI, right? RI divided RI plus RSI is the impact on RSI. That will change your internal gate voltage. Your source voltage remain GMVGS times RA. So after you find out RSI, your result will change it. That's why I say if I give you RSI, I give you RL, it will change your small signal equivalent circuit, right? I want you to draw a small signal equivalent circuit, write down equation according to your small signal equivalent circuit, then I know you understand the analysis. Right, do not copy the textbook solution saying, I have RSI, I have RL, I have everything, and then, but your problem doesn't have RSI, I delete RSI. This problem doesn't have RL, I delete RL, and then you give me the answer. So you are doing the comparison. I cannot say it's wrong, but it's not a good way to do it. So my statement was saying, please derive small signal equivalent circuit using original circuit, right? You have to show me the circuit. And use your small signal equivalent circuit to derive the answer for gain, input resistance, output resistance. You have to use equivalent circuit. So it's more custom design, custom made for that specific circuit. I may or may not have bypass capacitor, I may or may not have RSI, RL, I may or may not have RR, right? That's what I want you to analyze for me. So, right, that's in pain and clearly explained. And so we hope there's no loss in translation. Everything's clear. All right, additional questions? You already know two type of problems, I want to say. DC analysis, many good questions, right? DC analysis, chapter 4, AC analysis, you already know two problems. Yeah, very good. The good news, no frequency response. So